Hey, grade 12s. Cool. So if momentum is getting a bit tricky at this stage, we're about to break down question 5 of the Physics June 2025 paper. We're going to see the whole structure of a question like this, see the application of momentum, as well as some vector diagrams and change in momentum, i.e. impulse. So let's jump right in. So question 5 says, the vector diagrams below show the momentums of car A, mass 2,000 kilograms, which is traveling to the right, before and after a head-on collision with stationary car B. Cool. Then it says the collision lasted 0.5 seconds. Okay. After the collision, car B moves to the right with a speed of 20 meters per second to the -1 to the right. Okay. So the diagrams below are not drawn to scale. Vector diagram for car A before and after the collision. So we have an initial momentum of 30,000 kilograms per meters per second to the right. And then we have a final momentum of 10,000 kilograms per meters per second to the right. Okay, at this stage, before we start to break down the application of these questions, we're jumping into a theory question. 5.1 says, state the principle of conservation of linear momentum in words for 2 marks. So this one is quite a nice one. So what we have is the total linear momentum of an isolated system remains constant. So this just earned us 2 marks over there. The total linear momentum of an isolated system. Okay, so it means that no momentum is lost in the system. It is only transferred from one to another, meaning that there is no friction or anything like that, air resistance, if we can compare it to another section like equations of motion or mechanical energy, for example. So the total linear momentum of an isolated system remains constant. This is either a 0 or 2 mark answer, all or nothing as far as the way that we get marks for this answer. Okay, at this stage we are on 5.2. Calculate the 5.2.1 velocity of car A before the collision. Okay, so this was before the collision, the initial. This was after the collision. So we need the velocity of the car. We have our formulas up here. So the one that we want to work with is this guy over here, because we are just isolating it. We are working with one of the momentums, not the change in momentum. So we can just go ahead, write this formula down and solve for the velocity of the car. So P equals mv. This is our momentum. They've given us the momentum over here, and they have taken right as the positive direction, which means if anything is going to the left, that'll be a negative. So we can write 30,000 over here. Cool. Our mass of car A is 2,000 kilograms over here, and the velocity, the initial velocity, is what we want. So we can just go ahead and divide both sides by 2,000, and our answer for the initial velocity is 15 meters per second to the -1. Right. Okay, so we went 30,000 divided by 2,000, and this was our final answer for the initial velocity of the car before the collision. We're on 5.2.2 over here. It is asking us to calculate the mass of car B for 4 marks. So 5.2.1 was just using the momentum formula, but 5.2.2 has to do with the principle of conservation of linear momentum. What we want to look at when something is 4 marks, it means we're looking at the momentum before and our momentum afterwards. So what this means is that we need to add up the 2 different objects before the collision, counting for their mass multiplied by their velocity, and this mass multiplied by this velocity. So this is car A over here, and this is car B. This is the before scenario. I will erase some of this just now. So this is before the mass and velocity of car A plus the mass and velocity of car B. We're going to equate that to the mass and velocity of car A after the collision and the mass and velocity of car B after the collision. At this stage, we would have enough variables for everything else but the mass of car B, as that will be the missing factor on both sides. And then we can go ahead and solve for that. So that means I'm just going to write the mv plus mv over here, and then we can start to isolate it. Reminder, this is before, this is afterwards, and this is car A, this is car B. Okay, so car A's mass is 2,000, we know this, and its initial velocity before is 15 meters per second. That is what we calculated just now in 5.2.1. So we have the momentum, the mass times velocity of car A. Now we need to add the mass times velocity of car B. The mass of car B is what we want. We don't have that, and its initial velocity is 0. A reminder that it said collided with a stationary car B. So it was initially 0 before these 2 cars bumped into each other. So this was A before, this was B before, this is A afterwards, and this is B afterwards. So we have the befores, and now the afterwards is what we need. So the mass of of car A after the collision is still the same. So we have 2000 over there, but the velocity we don't have up here. But just like this previous question, we can calculate it considering we have the momentum after the collision. So we can just quickly go ahead and change this previous formula. Okay, so we just quickly changed this formula, which means our momentum after the collision is 10,000, also to the right, which means it is a positive 10,000. And then the mass of the car is still 2,000 over there. And now we are going to get the final velocity. And if we go ahead and divide these two things, we get 5 meters per second to the -1 right. And then we can go ahead and plug the 5 in here on the right side of our equation, as we now have the velocity of car A after the collision. And then at this stage, we are on car B after the collision. Car B's mass is still what we want over here, but its velocity was given to us. It says after the collision, car B moves to the right, also positive direction like these guys, to the right, with a speed of 20 meters per second to the -1. So at this stage, we have plugged in everything that we need to in order to solve for m here, as this m over here multiplied by 0 will just be 0 and disappear. So we can go ahead and simplify this. 2000 multiplied by 15 is 30,000 over there. This disappears. 2000 multiplied by 5 is 10,000 over there. And then m multiplied by 20 is just 20m. Okay, we can take the 10,000 over. So 30,000 minus 10,000 is 20,000, and that equals 20m. And then 20,000 divided by 20 is 1,000 kilograms. And that is the mass of car B. So we just earned 4 marks over there. So we're on 5.3. It says draw a labeled vector diagram showing the magnitude and direction of the change in momentum of car A. So car A is what they had over here, is what they plotted here with its momentum and momentum. Change in momentum is our delta P over here, which means it is the final momentum minus the initial momentum. So that means we're dealing with delta P. We have 10,000 because that is our final momentum going right, minus 30,000 also going right, which means we have negative 20,000 kg dot m dot s to the -1. So that is the magnitude. And if the change in momentum is negative, it means it is going to the left, because it was going fast this way to the right, but then it slowed down, still going right, which means this change in momentum opposed the initial direction that it was going. So that means we have a line going to the left, and we just have 20,000 kg dot m dot s to the -1 over there. That is our magnitude, that is our direction, and this is our final answer, earning us 2 marks. Cool. And then 5.4 says calculate the magnitude of the net force that car A exerts on car B. So we're just looking at car A here, and the net force is this formula up here. It is our F net delta T equals our change in P, our change in momentum over there. Okay, so we are going to use this formula here. So I'm just going to write it down so long. So F net is what we want. So we do not have that yet. Delta T over here was given to us. It was 0.5 seconds. That's what they said up here. The collision lasted 0.5 seconds, so we can just plug that in over here. And then delta P is what we calculated previously, but we can just go ahead and write that again. So it is the change in momentum, which means it is the final momentum minus the initial momentum. So it is 10,000 minus 30,000 over there. So then we can just solve for this. 10,000 minus 30,000 is minus 20,000, as we had already. And then we can divide by the 0.5 over there, leaving our F net as the only thing on the left side. And that means our final answer for F net is minus 40,000 newtons, which just means it is 40,000 newtons to the left, considering negative is to the left, but they only asked for the magnitude, not the direction. So we can just leave our answer here, and we are done with this question. So we just earned 3 marks over there. Okay, so 5.5, the last question of this section. It is a theory question, and it says, use the impulse momentum theorem to explain how an airbag, which inflates between the driver and the steering wheel of a car during a collision, protects the driver. So this is 3 marks, and it has to do with that last formula that we were using for 5.4. So I'm just going to rewrite this formula down here. We are given this formula on our formula sheet, and if we go ahead and manipulate the formula, so we take our delta T to the bottom over there, so it is delta P divided by delta T, we can then start to interpret this question a lot easier. Because what happens in a car crash, just like we have been working through in this scenario here, is that there is a large amount of force applied applied during a car crash, and that large amount of force can cause a lot of damage or injury to the driver. So an airbag is given in a scenario like this to increase the contact time, which helps protect the driver. So the bigger the number we have at the bottom, if we increase the time, the smaller the force applied, which means there is less impact, less force on the driver, and therefore less damage done to the driver. So all that we need to know is that our F net is inversely proportional to delta T. Therefore, the airbag increases contact time and therefore decreases the F net. And that would earn us 3 marks, showing that we understood that an increase in the contact time decreases the F net and therefore protects the driver during a collision. So that is our final answer over there for 5.5, and that is the whole section on momentum and impulse. Great job, guys. Let me know if there are any questions in the comments below, and otherwise I will see you in the next video.